This video is part 1 of a series about using simple continued fractions to solve linear Diophantine equations. We'll briefly discuss Diophantine equations and then set up examples that we'll solve in a later part. Let's get started. Linear Diophantine equation might sound like a fancy term, but the idea is really kind of simple. Let's discuss a couple of scenarios which I hope can make you see that the idea really is pretty simple. Suppose you have some pennies and nickels and you want to buy something that costs, say, 37 cents. What combinations of pennies and nickels can you use? We can write an equation to represent this. 5x plus y equals 37. X is the number of nickels and y is the number of pennies. X and y stand for numbers of coins, so when we solve this equation, we only care about solutions that are integers. We can't pay with fractions of coins. Focusing exclusively on integer solutions makes this a Diophantine equation. 7 nickels and 2 pennies works. 6 nickels and 7 pennies works, and of course there are other combinations. In fact, there's an infinite number of solutions to this equation. You might not think so at first, but there are infinite solutions if we allow for overpaying and getting back change. For example, you could pay with 8 nickels and get 3 pennies back as change. X would be 8 and y would be negative 3. However, if the scenario specifies paying with exact change, we'd rule out combinations like this, and there'd be a finite number of integer solutions. With this equation, depending on the scenario, there could be an infinite or finite number of solutions. But it's a linear Diophantine equation either way. Here's a similar scenario. Suppose you have nickels and dimes instead. What combinations of nickels and dimes could you use to buy something for 37 cents? The equation is 10x plus 5y equals 37. X is the number of dimes and y is the number of nickels. This time there aren't any integer solutions. If all you have is nickels and dimes, you can only pay amounts that are multiples of 5 cents. No combinations add up to 37 cents. This highlights a rule about linear Diophantine equations. In order for there to be solutions, any solutions at all, the greatest common factor of the coefficients, in this case of x and y, must also be a factor of what's on the right-hand side. In this example we just looked at, the greatest common factor of the coefficients, 5 and 10, is 5. So what appears on the right-hand side would need to be a factor of 5 in order for there to be solutions. It isn't, so there are no solutions. Now we'll talk a little about what we'll do with equations like these using simple continued fractions. We'll zoom out so we can see the whole whiteboard, and we'll zoom back into the middle. Our objective is to use simple continued fractions to solve linear Diophantine equations. The form of the equation will be ax plus or minus by equals plus or minus c. A, b, and c are positive integers, and also a and b are coprime. This means their greatest common factor is 1, which keeps us from violating that rule we just mentioned, that the greatest common factor of the coefficients must also be a factor of the right-hand side. By requiring that a and b are coprime, we know that their greatest common factor will be 1, so it will be a factor of c. When you're solving these equations with simple continued fractions, you have to be careful about the signs. We have 4 different variants. Ax plus by equals positive c, and ax plus by equals negative c. Ax minus by equals positive c, and ax minus by equals negative c. As we'll see in coming videos, each of these sends you down a slightly different path in the solution process. You need to be careful, or you might slip up and go down the wrong path and get a solution that would be correct, except it's for the wrong variant. Some good news, these 4 variants are all we need. If you're wondering about variants involving minus a, don't worry, we didn't sacrifice any generality by omitting them. If you find yourself with an equation that has minus a, you can multiply all the terms by negative 1 and end up with one of the variants we already listed. As an example, if you have minus ax plus by equals positive c, you can multiply through by negative 1, which changes it to ax minus by equals negative c, a variant that we already have. Let's move on and discuss the examples we'll solve in upcoming videos. We'll have a equals 101, b equals 27, and c equals 540. A and b are coprime, they don't have any common factors other than 1, so there will be solutions. Notice that b is a factor of c. That's perfectly fine. We'll solve all 4 variants. We'll show 2 of them on this first set of axes. Like usual, x is on the horizontal axis and y is on the vertical. The graph runs from x equals -100 to +100. Here are lines based on 101x plus 27y. The black line is for when the right-hand side is positive 540, and the red line is for when it's negative. We are looking for integer solutions though. These dots are the combinations within the axes when both x and y are integers. We can take away the line. What we'll do is use simple continued fractions to find the integer combinations of x and y that satisfy the equation, some of which are shown with the dots here. Here are lines for the other two variants, the ones based on 101x minus 27y. Once again, the black one is for when the right-hand side is positive, and the red one is for when it's negative. Since we're just looking for integers, we'll show the dots and remove the line. Again, in upcoming videos we'll use simple continued fractions to find the integer solutions to the equations, some of which are shown on this graph. This covers all the variants. These two are here, and these two are here. In this video, we talked a little about linear Diophantine equations and set up the examples that we'll solve in upcoming videos. That's all for now.